Okay, so we looked at Bohr's atomic structure, where we stated that electrons would orbit around this positive nucleus, and the electrons would orbit around the positive nucleus in these orbits called electron shells. However, we also looked at some of the limitations of this model, specifically that Bohr did all of his experiments on hydrogen when he created the model, and hydrogen only has a single electron, versus it does not actually explain some of the polyelectronic systems of the atoms or elements. And because of this reason, he didn't actually see some of the energy levels in between energy shells, right? So he didn't look at subshells, the presence of subshells. So a more descriptive notion or model of the atom actually occurred later, after Bohr, by a scientist. His name was Erwin Schrödinger, right? So Schrödinger actually described electron in, well, he described electron locations using probability density equations. Right? And these density equations, these probability density equations, it basically looked at the probability of finding an electron in a given amount of space. Right? So the probability density equations that Schrödinger created, he basically looked at finding an electron in a certain region of space and the probability of that electron. The whole notion here is that electrons are constantly moving, so you can't actually pinpoint the electron's position at any given time, right? And this was also indicated by another scientist. His name was Heisenberg, and Heisenberg's uncertainty principle stated that an electron's position cannot be pinpointed at a specific instant in time because of the fact that an electron's velocity is massive. Right, so it doesn't make sense for us to look at a position of an electron because that position is changing. Rather, we look at a map of the area where we'd most likely or most probably find an electron. Right, so these probability density maps were really useful, right? So these probability density maps were really useful in pinpointing where an electron would most likely be found, right? So based on these two things, we then had the creation or this notion of an orbital. Okay, orbitals are basically areas of space in 3 dimensions, so 3D space, which most probably contains an electron, right? An orbital is any region of space that can hold, that you would most likely find an electron, and orbitals can include up to a maximum of 2 electrons. So you can actually find up to 2 electrons in each orbital. And there's different types of orbitals, and an orbital is, once again, a mathematical equation. It's a probability density map, right? And there's different shapes of orbitals, but each orbital can only hold a maximum of 2 electrons. Now the different shapes of orbitals include a spherical orbital, so I'm going to draw it in 2 dimensions as a circle, right? But you would expect this to be a sphere, right? So like this would basically be a sphere. Right, so this is, or you would expect it to be a sphere, right? But we call this the s orbital, the spherical orbital, right? And in the middle of the orbital, we should find a region where there is 0 electron density. We're going to call the 0 electron density a node, and that's essentially where the nucleus should be located. Okay, so any area around this node, we would expect to find an electron. Now, the reason we use a circle, the reason we look at the edges, because we outline the edges because this is the highest probability of finding an electron. So at the edges, we have the highest probability of finding an electron, right? So if you look at this as being a probability density map, right, and we look at the orbital as just pinpointing or finding the location of an electron from the node, whoops, okay, we can understand that. I'm going to use large densities in orange, right? You're going to see that most of the density is out in the circumference. Okay, so you can see that there's going to be a darker orange out in the circumference, and then we can see that density will wane off as we get closer to the node, right? So the node would have 0 density. So there's larger electron density, so you'd most likely find an electron out here in the outer regions of the orbital, right? Versus there's less electron density closer to the nucleus, right? So because of that, we usually draw the outline of the orbital because of the fact that most of the electron density would be found on the outside of the orbital, right? So an s orbital is one type of orbital, but we're also going to be looking at a p orbital, right? It's usually a dumbbell-shaped orbital, right? So a p orbital is going to be a lot larger than an s orbital, right? And then we can also look at d orbitals and f orbitals, right? You'd have to view these in 3 dimensions, right, to actually see it. So we're not going to really look at that. However, we need to understand that in terms of the energy of orbitals, we know that energy of an electron is associated with its relative distance from the nucleus, right? So the larger the separation distance from the nucleus, the weaker the force of attraction, and as a result, the higher the kinetic energy of the electron. Well, we can understand that the energy of an s orbital is the lowest, and it's therefore the most stable. The p orbital itself is larger in energy than the s orbital. The d orbital itself is larger in energy than the p orbital, and the f orbital itself is larger in energy than the d orbital. Each of these orbitals represents a path length of the electron from the nucleus. So this has essentially, the s orbital has the shortest path length, and the f orbital has the highest or largest path length. Okay, let's use the word largest instead. So this guy actually has the largest path length, right? So if the s orbital, if this is the nucleus, and I'm just going to kind of draw this out, if this is the nucleus and this is the s orbital, and the electrons are found orbiting most likely on the circumference of the s orbital, the p orbital, which I'm going to draw in red, let's do green, the p orbital is going to be a lot further from the nucleus, right? So the p orbital, you can see that the path length is further from the nucleus, and as a result, the electrons that orbit in the p orbital is going to be further from the nucleus and therefore have more energy, more kinetic energy, right? So the shape of the orbital just represents the path length of the electron orbiting around the nucleus. The larger the path length, the more energy that the electron has because it's further away from the positive force of attraction, and vice versa, right? So that's why the p orbital has higher energy than the s orbital, d orbital has higher energy than the p orbital, the f orbital has a higher energy than the d orbital. Each of these represents a different shape of the orbital, which just basically represents a different shape of the orbit, really, right? It's like looking at the planets, right? Pluto has a different orbit than the Earth's orbit around the sun, right? So these electrons just have different orbits. So it's very important to understand this notion of orbitals, and each of these orbitals, they hold a maximum of 2 electrons. So it doesn't matter if the electrons are found in an s orbital or a p orbital or a d orbital, they all hold a maximum of 2 electrons, right? So you can have a maximum of 2 electrons in an orbital, and there's 3 ways you can look at an orbital. We can look at an orbital as an empty orbital. I'm going to use circle for orbitals in this case. You can have an empty orbital where you have no electrons. You can have 1 electron. It's called a half-filled orbital. And you can have 2 electrons in an orbital, which is the maximum number of electrons, and then we call this a spin-paired orbital. So I'm going to explain the difference between all 3 of them. Specifically, we need to understand why orbitals that electrons that maximally fill orbitals are spin-paired, in the sense that they are actually spinning in opposite directions. So I'm going to explain that next. Okay, so we described orbitals as probability density maps that house electrons. Right, and we looked at different types of orbitals depending on the shape, and the shape of an orbital just represents the path length of an electron around the nucleus, right? And our notion here, we use this description of an orbital because electrons are moving really quickly. We can't actually pinpoint the electron's position at any instant in time because the velocity is too great. So as a result, we have to look at a large segment of area where we'd most likely find an electron. So the types of orbitals that we looked at, so the orbital types included the s orbital, the p orbital, the d orbital, the f orbital. There are more types of orbitals. There's the g and the h orbital, but it's not important. And basically each of these orbitals have a different shape, right? So we looked at the p orbital and the s orbital. The p orbital has this dumbbell shape. A d orbital is going to be found in 3 dimensions, so I'm not going to really look at these too well. Okay, so I'm not going to really look at these orbitals. However, we need to understand that each of these orbitals have a region of 0 electron density, and the region of 0 electron density is called a node, right? So the node is basically where you could find the nucleus. So 0 electron density, right? And we also noted that the energy of these orbitals followed that the f orbital out of these 4 is the highest energy and the s orbital is the lowest energy, and this is associated with the relative distances, right? The separation distance of the electrons in the nucleus of the f orbital is basically going to be the highest, and the separation distance of electrons in the s orbital from the nucleus is the lowest, right? So this is very important, and we also noted that each orbital can hold a max of 2 electrons, right? And this is true for all orbitals, right? One orbital has more energy than the other due to its path length, right? The orbit length that each electron will undertake around the nucleus. Now, we stated that orbitals can be either empty. This is an empty orbital. I'm going to use circles for each orbital, right? And you can also have a half-filled orbital. Right? I'm going to show electrons using these arrows, right? And we can also have a spin-paired orbital. Okay, so let's look at the relationship between each of these, right? So you can understand that you can view electrons as these little tiny magnets, right? And an electron is a negatively charged particle. It's really small, and it's moving, right? So electrons should create an electrical field, but we know that moving charges also constitute a magnetic field. So electrons create an electrical and a magnetic field, and these electrons, how they move, they actually spin, they orbit, right? So electrons can either spin counterclockwise, so the electron can spin this way, or electrons can spin clockwise. Okay, so the electrons can also spin this way. And when electrons spin in opposite directions, they create opposite magnetic fields, right? So what happens here is that the direction of spin will affect the magnetic field that it creates. Now, electrons that occupy orbitals prefer to be half-filled. Oops. And the reason electrons prefer half-filled orbitals is because electrons, when they get too close to each other, when they get too close in the same vicinity, they repel each other, right? Two like charges will repel. It's kind of like, the analogy here is if you have 3 seats on a bus, right, and one person is sitting on the far left seat, usually another person that's coming in to fill in one of the seats, they're not going to sit right next to the person. They'll usually sit 1 seat away, right? So it's the same idea with electrons, is that electrons prefer to be by themselves. When 2 electrons get too close together, there's a repulsion force, right, which makes the orbital very unstable. So this is actually a more stable orbital. This tends to be more unstable, more reactive, because of the repulsion forces, right? There is some kind of repulsion, electron repulsion, that occurs here. Now, in some cases, well, in most cases, electrons need to occupy, 2 electrons need to occupy the orbital. So in the case where 2 electrons need to occupy an orbital, what the 2 electrons will do is they'll actually spin in opposite directions, right? So when orbitals need to include 2 electrons, the electrons will spin in opposite directions. And when the electrons spin in opposite directions, they have opposing magnetic fields. Right? And when they have opposing magnetic fields, they actually reduce the electric field, the electric force of repulsion. So they actually reduce the electric force of repulsion when they have opposing magnetic fields, right? So this process, where the 2 electrons are spinning in opposite directions, this process is called spin pairing. So electrons will be spin paired. Electrons will be spin paired when 2 electrons have to occupy an orbital, and we know that each orbital can hold a maximum of 2 electrons, right? And spin pairing is where the 2 electrons will spin in opposite directions, and we can show this by using an upward arrow and a downward arrow. Now, the upward arrow doesn't mean clockwise or counterclockwise. It just means that if I say that this is clockwise, then this has to be counterclockwise, because it means it's an opposing spin. But if this is a counterclockwise spin, then this is clockwise. So it just means that they're both opposite, right? And spin pairing, what the electrons will do when they spin in opposite directions, they actually reduce the electrical field of repulsion, right? The electrical force of repulsion. So that's what keeps the orbital much more stable than it can normally be, right? So you need to understand the difference between empty, a half-filled, and a spin-paired orbital. Specifically, the spin-paired orbital is where the electrons that occupy the orbital will fill it to its maximum capacity, and they spin in opposite directions to reduce the repulsion force between the 2 electrons. So the quantum mechanical model of the atom, the basic unit of the quantum mechanical model is the orbital. Okay, so the orbitals are what compose, they're basically the single unit of this quantum mechanical model. And we know that orbitals are basically probability density maps of finding electrons, and electrons can occupy orbitals to a maximum of 2 electrons per orbital. And we looked at the different types of orbitals, right? The s, the p, the d, the f orbitals, to name a few. Now orbitals, so electrons are going to be found in these orbitals, right? So let's say that electrons are found in these orbitals, and these orbitals actually will come together to form combinations of orbitals, and these guys are actually called subshells, right? So because subshells are made up of combinational orbitals, we can also have s, p, d, and f subshells. So I'll explain what subshells will look like. And then these subshells actually combine and they form energy shells. Okay, so each energy shell can have a multitude of different subshells, right? So we're going to start by looking at electrons organized in orbitals. And then the orbitals will come together and then they will form these subshells, and the subshells will come together and form energy shells. Now let's take a look. So we looked at what orbitals are, and we looked at the different types of filling of orbitals. Let's take a look at subshells. So subshells are combinations of orbitals. Okay, and subshells are indicative. They're basically named by the type of orbital that they are composed of. And furthermore, subshells will also include a certain number of each type of orbital, right? So subshells are composed of a specific number of its particular orbital. Okay, and there are basically a few numbers you can kind of memorize through this. The S subshell, which is named after the orbital, and I'm going to create a really quick chart for this, right? So we'll have like the type of subshell, right? The orbital that is made up of, so the orbital type, and the number of orbitals for the combination. Okay, so the S subshell is made up of S orbitals, right? The spherical orbitals, we stated that it kind of looks like this, right? And the node is found here. Right, the S subshell is made up of the S orbital, and there are basically one S orbital that makes up a subshell. So an S orbital is effectively an S subshell, right? So there's one S orbital that you can have, right? We know that the number of orbitals, each orbital will hold a maximum of 2 electrons. So if we're looking at maximum, oops, let's use green for this. So say we're looking at max number of electrons that you can hold in each of these subshells. Because the S subshell only holds, the S subshell is basically composed of one S orbital, you can only hold a maximum of 2 electrons. Right? Because remember, each orbital can hold a maximum of 2 electrons. Now let's take a look at the P subshell. Now in the case of a P subshell, the P subshell actually is made up of P orbitals. So recall that a P orbital kind of looks like this. It's like a dumbbell shape, right? For the most part, we can draw out the S and the P orbital really quickly, but can't really do that for the D and F because they're more 3 dimensions and they involve planes and so forth. Now, in this case, for the P subshell, we actually have 3 P orbitals that make up the P subshell. So I'm going to show you guys what this will look like, right? But because there's 3 P orbitals that make up the P subshell, each orbital can hold 2 electrons, so we can actually hold 6 electrons in the P subshell. In the D subshell, we can basically hold, we have D orbitals that make up the D subshell, right? And the D subshell will look a little funky to draw. It's kind of hard to draw this in 2 dimensions. Let's draw like this clover leaf, right? And we have a node here, so I can't really draw this in 2 dimensions. But the D subshell actually holds 5 D orbitals, right? So this guy holds 5 D orbitals. The P subshell holds 3 P orbitals. The S subshell holds 1 S orbital, right? Because there's 5 D orbitals that make up the D subshell, we can hold a maximum of 10 electrons, because each orbital can hold a maximum of 2 electrons. The F subshell will be composed of F orbitals, And this one also kind of looks funky. You can't really draw this in 2 dimensions. Drawing it like this, it looks like this like pacifier. And let's say that the node is like somewhere here, right? And the F subshell can hold a maximum of 7 F orbitals, and each orbital holds a max of 2 electrons, so we can have a total of 14 electrons in the F subshell. Okay, so what I'm going to do next is I'm going to illustrate what a P subshell looks like, and I think I'll give you a clearer picture of what these subshells really are. Okay, so we stated that subshells are basically combinations of orbitals, right? And each subshell is named after its type of orbital that it's composed of, and each subshell also has a specific number of orbitals that it's made up of, right? So we looked at the S, the P, the D, and the F subshell, and I would tell you guys to review the previous video to kind of understand how many subshells, how many orbitals, for each subshell that it's composed of, right? How many of its own particular orbitals it's composed of, and how many electrons that it can hold in total. We said that the P subshell, I'm going to show you guys the P subshell to demonstrate this. The P subshell is made up of 3 P orbitals. So it's made up of 3 P orbitals and can hold a maximum of 6 electrons, because we know that each orbital can hold a maximum of 2 electrons. I'm going to demonstrate what the P orbital will look like, and for me to do this, I'm going to do this in 3 dimensions. So because I'm going to do this in 3 dimensions, I'm going to draw out the XY plane, XYZ plane, right? So this is the x-axis, this is the y-axis, and then this is the z-axis. So because we're looking at this in 3 dimensions, we need to look at all 3 dimensions when we're constructing this on our page, right? So we can notice that this is negative x, right? This is negative y, this is negative z, and you would be more aware of this if you took calculus and vectors. But basically the P subshell is a combination of 3 P orbitals. I'm going to draw each orbital on each of the planes, right? So there's going to be one of the P orbitals on the x plane, shown here. And remember that P orbitals look like this dumbbell shape, right? So I'm just going to draw that out. Right, we drew P orbitals initially using this dumbbell shaped, right, and the node here exists in the middle, right, so this is the node. Okay, so I'm going to draw P orbitals on each axis. Okay, so this is one of the P orbitals. We said that the P subshell is made up of 3 P orbitals, so one of the P orbitals is located on the x-axis. The second P orbital is located on the y-axis. I'm going to draw it here. They're on different dimensions basically. Okay, so the other P orbital is located on the y-axis, and the third P orbital is located on the z-axis. So these guys are all 90 degrees apart. Okay, so these guys are 90 degrees apart. Draw that here. Okay, and basically we can label each orbital based on what axis they are located on. So this is basically the px orbital, right? So this full thing here is the px orbital. This is basically the py orbital, and in green we have the pz orbital. Okay, so this is the pz orbital, and we can notice that they're basically 90 degrees apart from each other, right? The x, y, and z axes, they're 90 degrees away from each other, right? And each of these orbitals, they hold a maximum of 2 electrons. Like you have a maximum of 2 electrons here, a maximum of 2 electrons here, right? And the maximum of 2 electrons here, right? So each of these orbitals can hold 2 electrons. The subshell, this whole thing is the P subshell. So what I just drew here is the P subshell. It's made up of 3 P orbitals, right? So you can write down Px, Py, Pz. All of this makes the P subshell. And that's why the P subshell can hold 6 electrons, because each orbital can hold 2 electrons, right? So instead of drawing it like this, and this is just the graphical representation, but instead of drawing it like this, we want to write subshells. What I'm going to be demonstrating later when we draw out the quantum mechanical model, I'm going to draw it out like this. And this whole thing here is the P subshell, and we can basically look at each of these orbitals as Px, Py, and Pz, and you can have empty orbitals, You can have half-filled orbitals, or you can have spin-paired orbitals, right? So this is spin-paired. This is half-filled, and then this is empty. Okay, so this is a representation of a subshell, right? I use the P subshell because it's much more easier to look at than the D subshell, the F subshell. You would probably need some kind of you would kind of need some kind of 3D imaging animation. But this will kind of give you an understanding of what a subshell is, right? Once again, it's a combination of orbitals, and it's really important to memorize how many orbitals make up each type of subshell and how many electrons that subshell can hold. Okay, we described the quantum mechanical model as containing electrons located in these regions called orbitals, and orbitals are these probability density maps that we use to look at an electron's location around a nucleus or a node, which is called any region with 0 electron density. And in this case, orbitals actually come together, and we looked at the different types of orbitals, the S, the P, the D, and the F orbitals. These orbitals, and each of these orbitals have different path lengths, right? We looked at the energies, right? The P orbital has a higher energy than the S orbital, the D orbital has a higher energy than the P orbital, the F orbital has a higher energy than the D orbital. And we looked at these energies of these orbitals, which have different path lengths, and the combinations of these orbitals in the form of subshells, right? So subshells are combinations of different orbitals, specific types of orbitals with different number of each. And the subshells are actually named after the types of orbitals that they're composed of. So the S subshell, the P subshell, the D subshell, and the F subshell. I illustrated the P subshell for you guys, excuse me. And it should give you an idea of how we can look at these subshells as just combinations of their individual orbitals. And now what we're going to be looking at are electron shells. So electron shells are combinations of subshells. Now, electron shells don't just have a single subshell, they can have multiple subshells. So how I'm going to illustrate this is by creating a chart, and you can see this chart here. We're going to look at each of these energy shells. So remember that Bohr looked at electrons in an atom as orbiting around the nucleus in these orbits called shells. Well, this is basically how he looked. These are basically the electron shells that Bohr actually looked at, right? So let's start with the first energy shell. In the first energy shell, I'm going to use N as my shell number here. Okay, so N is my shell number. N is the shell number. And what I'm going to be looking at is I'm going to be looking at all of the subshells and orbitals in each of the particular energy shells. All right, so let's start with the first energy shell. So N is equal to 1. The subshell that's found in the first energy shell is only the S subshell. We know that the S subshell contains S orbitals, and we know that each S subshell only contains one S orbital. Okay, so there's only going to be one S orbital that is going to be found there, right? So we'll call it 1s orb or something. Okay, so because an S subshell only contains one S orbital, the maximum number of electrons that an S subshell can hold is 2 electrons. Because the first energy shell only has one S subshell, then as a result, the first energy shell can only hold 2 electrons. So that's why the first energy level can only hold 2 electrons. It only has one S subshell, right? Now, and this is consistent with Bohr's model, right? So when we looked at the nucleus and the first energy level, right? This is N is equal to 1. You would only see a maximum of 2 electrons being held there. Now in the second energy level, or the second energy shell, right, what you're going to notice here is that this guy's actually going to have an S subshell as well as a P subshell. And because this is found in the second shell, we need to actually write down the number of each level, right? So in the first energy level, we write that the S subshell that's found in the first energy level is called a 1s subshell. Okay, so the 1s subshell is the S subshell found in the first energy level. In the second energy level, because it's found in a different shell, and we're going to actually look at it here, so the shells are actually further away, and the subshells are actually found within the shells, right? In the second energy level, we actually have a 2s and a 2p subshell. right? So we can actually represent each of these subshells, right? When we look at subshells, we represent subshells as n of the particular subshell. So we'll call the subshell x or something, and x is a particular subshell, and n is the energy level of the subshell. Okay, so n is the energy level of the subshell. Okay, so we can look at each subshell as nx, right? And in this case, the second energy level, the second shell, has the 2s subshell and the 2p subshell, right? Now in the 2s subshell, we can have s orbitals, because an s subshell is made up of s orbitals. In the 2p subshell, we can have p orbitals. We stated that in the s subshell, we should have a maximum of one s orbital, right? And one s orbital means that we'll have a maximum of 2 electrons. However, in the 2p subshell, we'll actually have 3p orbitals, right? We'll have 3p orbitals, and because each orbital can hold a max of 2 electrons, we can have a total of 6 electrons. So in total, you guys can actually see that this is going to give us 8 electrons. That's why we can have a maximum of 8 electrons in the second energy level. So this is something that Bohr didn't really understand at the time. The quantum mechanical model will help us to understand that a bit further. In the third energy level, we'll have a range of 3 subshells. I'm going to use a different color for this to demonstrate that. Right, so the third energy level is further away. Right, so the third energy level is even further away from the nucleus. So the subshells in the third energy level are going to have more energy than the subshells in the second energy level. Right, so we're going to actually see an s subshell, a p subshell, and a d subshell. And you can notice here that I'm using the number 3 in front of each subshell because this indicates that each subshell is found on the third energy level. In the s subshell, we have an s orbital. In the p subshell, we have a p orbital. In the d subshell, we have a d orbital. And we know that in an s subshell, we should have one s orbital. Right, in the p subshell, we should have 3 p orbitals. And in the d subshell, we should have a total of 5 d orbitals. Okay, so because one s orbital should have a maximum of 2 electrons, 3 p orbitals would have a maximum of 6 electrons. 5 d orbitals in the d subshell should have a maximum of 10 electrons, right? 5 times 2. And in total, we actually have 18 electrons. So in actuality, in the third energy level, we can actually hold a maximum of 18 electrons. Okay. If we wanted to look at the fourth energy level, I'm just going to use a different color for this. The fourth energy level, we're actually going to have 4 different subshells. So we're going to have the 4s subshells. There's an s subshell, there's a p subshell, there's a d subshell, and there's an f subshell. So in the s subshell, we have an s orbital. In the p subshell, we have a p orbital. In the d subshell, we have d orbitals that make it up. And in the f subshell, we have f orbitals. And the s orbital can hold a maximum of the s subshell, is made up of 1 s orbital. Right? The p subshell is made up of 3 p orbitals. The d subshell is made up of 5 d orbitals. And the f subshell is made up of 7 f orbitals. And the s subshell can hold a maximum of 2 electrons. The p subshell can hold a maximum of 6 electrons. D subshell can hold a maximum of 10 electrons. And the f subshell can hold a maximum of 14 electrons. So we add this up, we get 2 plus 8, which is 8. 2 plus 6, which is 8. 8 plus 10, which is 18. 18 plus 14, which is 32. So we actually have 32 electrons. Right? So in the fourth energy level, you would expect 32 electrons. Right? So this is basically the hierarchy of organization in terms of the quantum mechanical model, where electrons are grouped into orbitals. There's different types of orbitals which describe the path length of electrons around the nucleus. Each orbital will also have a particular energy relative to each other. And orbitals come together to form subshells. The subshells are named after the orbital that they're made up of, and each subshell is made up of a particular type of its orbitals, right, or a particular number of each orbital. And the subshells come together in different arrangements to form electron shells. So this is the hierarchy of the quantum mechanical model, and what I'm going to do next is I'm going to show you guys how to draw out the atomic structure in association with the quantum mechanical model. Alright, let's construct the atomic structure using the quantum mechanical model for the following element, so nitrogen 7. Right, because it's an element, we know that this guy has 7 electrons, 7 protons, and if you subtract the atomic mass, we're looking at chemical symbols in the form of the atomic number as a subscript, the atomic mass as a superscript, so it should also have 7 neutrons. Now, if we're looking at the quantum mechanical model, we can understand that the quantum mechanical model looks at electrons that are organized in orbitals, right, and the orbitals are organized in subshells, which are combinations of orbitals, and then energy or electron shells, which are combinations of subshells. Okay. Now, before we can actually look at the organization of these electrons and orbitals and subshells, eventually and subsequently electron shells, we actually need to look at a few rules, right? One of these rules is something called the Aufbau Principle, and the Aufbau Principle states that electrons occupy orbitals in atoms from lowest energy to highest energy. This is really important because orbitals make up subshells, and then subshells make up electron shells, so electrons will always occupy lower energy electron shells than lower energy electron subshells, and then therefore lower energy electron orbitals first before its higher energy equivalents. So what that means here is that we always fill electrons starting with the first energy level, the first subshell, 1s, then we fill the 2s subshell in the second energy level, then the 2p subshell, because we know that the p subshell has more energy than the s subshell, because the p orbital that makes up the p subshell is more energetic than the s orbital that makes up the s subshell. So then we fill the 2p subshell, then we go to the third energy level and we fill the 3s subshell, then the 3p subshell, then the 3d subshell, and so forth, right? So you guys can just kind of memorize this, right? But then there is an exception. So after the 3d subshell, we then fill the 4s subshell, and then the 4p. Oh, sorry. We actually fill 3p, then the 4s, then the 3d subshell. Okay, so there is an exception here. It's because of the fact that the d subshell actually, the d orbital actually spans further away than the 4s subshell. So it's actually further away than the next energy level, right? So you guys can just kind of memorize this, and it goes 4p. I will later show you how to memorize this using your periodic table, right? I think the quickest way that they'll show you in school to memorize this, if you write down all of your subshells like this, to find the order. Oh, sorry, a mistake there. This is 4D, 4F, 5S, 5P, 5D, 5F. Okay. So a really quick way of memorizing this, memorize this order of filling from lower energy subshells and orbitals to higher energy subshells, is you're basically filling it this way. Oops. Okay, so you follow the arrow here. I'm just gonna erase this, but the direction of the arrow should go this way. So you go 1s, you fill the 1s orbital, or the 1s subshell first, then you fill the 2s, then you fill the 2p, then the 3s, then 3p, then 4s, then 3d, then 4p, then 5s, then 4d, then 5p. So you can actually use this to memorize the filling, low energy subshells and its respective orbitals to high energy, right? So that's why this is really useful. So this Aufbau principle is really useful to kind of understand, right? And then the next principle that we need to also look at is Hund's Rule. Okay, And Hund Rule states that electrons prefer to be half-filled than spin-paired. Right, so electrons prefer to be half-filled than spin-paired, so you always half-fill orbitals before you spin-pair, right? So always half-fill first. Before spin pairing. Okay, so I'm going to demonstrate this by drawing the quantum mechanical model representation of nitrogen. Okay, so how I'm going to do this, I'm just going to clear some space here. So how I'm going to do this is I'm going to keep these rules here so we can take a look at it. But how I'm going to do this is I'm going to put energy on this y-axis, and then what I'm going to do is I'm going to put each of the orbitals, right? So what you want to do, you usually would measure this, but I'm going to start here. Oops, let's get rid of that. I'm going to start here at the base, and I'm going to put my first energy level. So this is n is equal to 1, right? And the first energy shell, we said that there's only going to be one S subshell, so this is technically the S subshell. So I'm going to use red for the S subshells, right? So red is the S subshell. Let's use orange for the P subshell, right? And in this case, what you're going to see here is in the S subshell, in the 1s subshell, so this is the 1s subshell. In the 1s subshell, you can have up to 2 electrons, right? Now you fill the first electron, the second electron has to be spin paired. Spin paired means that it's rotating or it's moving in the opposite direction, right? Now from between each of the energy levels, from the first energy level to the second energy level, there's going to be some kind of space, right? So I'm just going to using the grid system, I'm going to move up 2 spaces per shell, right? And this is your second energy level, so let's say this is n is equal to 2, right? And in the second energy level, in the second shell, we should have an S subshell and a P subshell. So here's my S subshell, right? We should also have a P subshell, and the P subshell has 3 p orbitals. So I'm just going to draw the P subshell here, and you can notice that the P subshell is higher in energy than the S subshell. And I'm going to draw the P subshell with p orbitals in orange. Okay, you always fill, according to Aufbau Principle, you always fill the S subshell before the P subshell, so 2s before 2p. So I'm going to fill 1 electron here, second electron, they're spin paired, right? So that's 4 electrons I've accounted for. Now nitrogen has 7 electrons, so I need to fill the other 3 in the P subshell, right? So this is 2s. This is a 2s subshell. This whole thing here is the 2p subshell. Okay. Now each p subshell has an x, a y, and a z orbital. So this is the px orbital, py orbital, the pz orbital, and you can call it 2px, 2py, and 2pz. Right? If you're looking at each individual orbital. Now there's 3 more electrons that have to occupy the p subshell, but according to Hund's rule, we always need to half-fill orbitals before we spin pair. So if we're half-filling orbitals before we spin pair, I'm half-filling them like this. Okay, so this is the atomic structure of nitrogen using the quantum mechanical model.